Yeah, okay, great. Thank you. Thank you so much to the organizers for this invitation to speak. And thank you everyone for coming. So today I'm going to talk about a characteristic P and a Frobenius version of the alpha invariant. So we'll get there in steps. And please feel free to interrupt to ask questions, but just note that I can't see the chat. So maybe someone else would have to like repeat the question to me if you put it in the chat. But um, okay, so we'll start with some background about why we would like to study the alpha invariant. So section 0 is some very broad motivation for why we want to study all of this. Uh, can you see my screen and the Jamboard? Just checking. Okay, great. Um, so let X be a smooth Fano variety over the complex numbers. Okay? And for us, that means X is projective, for now smooth, and later we'll relax the condition. And negative of the canonical divisor is ample. That's what it means to have a Fano variety. So one very broad question is, so when is X what is called K stable? Okay. So I won't say what this is, what the definition of K stable is, but except to say that it's an algebraic condition on the kind of degenerations X can have. Okay. So it's some numerical condition on the degenerations of X. And it turns out that this algebraic condition is actually equivalent to an analytic condition that there exists a Kähler-Einstein metric on X. So this was the content of the famous Yao-Tian Donaldson correspondence, which is now a conjecture, which is now a theorem. So this is almost true if I add the word poly, which is again some slight modification of K stability. So so there is an algebraic condition on the degenerations, which is equivalent to the existence of this analytic condition, which is the existence of Kähler-Einstein metrics. So that's one reason why this question is interesting. Okay. The other reason, which in the recent years has become clear, is that it turns out that K polystable varieties, so Fano varieties which are K polystable, can be parameterized by a projective scheme. So they admit a good moduli space, which is a projective scheme. Right? So they have a nice moduli theory. So it would be interesting to understand how to tell when a Fano variety is K stable or not. Okay? So that's the motivation for for what I'm going to talk about. So how to tell if X is K stable? I guess it's the same question. So the first progress in this direction was made by Tian, as far as I know. I think it was 1987. Tian introduced this alpha invariant, right, and proved the following theorem, which is called Tian's criterion now. So if the alpha invariant of X is bigger than n over n plus 1, where n is dimension of X, then X is K stable. So I'll give you a definition of the alpha invariant in the next section, but whatever it is, it's an invariant which is a sufficient condition for K stability, which provides a sufficient condition for K stability. Right? It's not a necessary condition, so it's not dependent on the F, and so it does not characterize K stability, but it provides a sufficient condition. So using this, I think Tian solved the problem for smooth del Pezzo surfaces, and maybe more. So that's the history of the alpha invariant. So I'm going to the next slide if you're looking at the Jamboard. So now let's talk about what this alpha invariant is about in the complex version. Okay, so classically, so Tian defined the alpha invariant in terms of some coefficients that occur in PDEs, I think. I don't really understand that much. So, but later on, it was proved to be equivalent to another invariant, which can be thought of in terms of singularities of divisors on X. Right? So in this talk, for now, let's talk about KLT singularities. Okay. So this is the singularity of a pair X delta. And for that, by that, usually mean X is a normal variety. Delta is an effective Q divisor on X. We will also usually assume that Kx plus delta is Q Cartier. There's a technical condition. If you don't know what that means, you don't have to worry about it. It's automatic on smooth varieties. So KLT singularities, maybe I'll not go into the definition because it's technical and I don't have time and we won't need it. But I'll say that it's defined using log resolutions of X delta. So it's a resolution of singularities of this pair X and delta. So it's just a birational model on which this pair becomes looks like a simple normal crossing divisor, basically. Right? And KLT is roughly saying that the log resolution is close to the original pair. Right? So if the resolution of singularities somehow matches the original pair closely, that's what it means roughly to be KLT. Okay, you have to look at coefficients, and I won't go into the technical definition. So it's a very nice class of singularities, and so on which we can basically run the minimal model program, and that's where the first arose. The other invariant I want to talk about is the log canonical threshold, LCT. So this of a pair, log canonical threshold, it's a numerical invariant, which is the supremum of all non-negative rational numbers t, such that x comma t delta is KLT. So it's just measuring how far delta itself is from being KLT. So if t is strictly bigger than 1, that means x delta is KLT. But if the log canonical threshold is strictly bigger than 1, but if it's smaller than 1, then it's not KLT. But if you put a smaller coefficient, it becomes KLT. Okay, so with this, I can tell you, we'll draw a line here. The alpha invariant of Tian and later reinterpreted by Demey. So Demey was, I think, the one who showed that these two definitions are equivalent. Anyway, this is what we'll use as our definition. So now this definition works whenever x is also KLT. So it's a Fano variety where this means x comma 0 is KLT. Let me go to the next slide. It will be easier there. I'll go to the third slide. So Tian and domain say x be a KLT Fano. So it's still a projective variety. Negative of the canonical divisor is ample. Maybe it's only a Q divisor, but it's still ample. And x is KLT means that the pair x comma 0 is KLT. In this case, the alpha invariant of x can be defined as follows. So we can think of this as supremum of all non-negative t's such that x comma t times d is KLT for every effective Q divisor d such that d is Q linearly equivalent to the anti-canonical divisor. So this is one way to think about what the alpha invariant is. So it's the smallest coefficient. It's like the, or it's the supremum of all coefficients you can put in front of any anti-canonical Q divisor such that the pair remains KLT. This is another way of thinking about it. And the idea is, since anti-canonical divisor, the anti-canonical is ample, right? So that means there are many, many Q divisors linearly equivalent to negative KX. And in some, that's why it's a very big, okay, sorry, let me say that. So another way of thinking about it is it's the infimum over all n, and another infimum over all divisors, this time not Q divisors, but just the negative nkx linear system. And there will be many such divisors. And then we take the law canonical threshold of this pair xd. But then since we are taking a degree n divisor, you have to scale it up by n, right? So a high degree divisor is going to have a low law canonical threshold typically. So you scale it up back and then take an infimum and try to find the worst possible. And what I was saying is that it's an infinite infimum. So it's somehow an infimum over like an infinite set. Or infinite family of divisors, not just an infinite set. So, so that's the alpha invariant. So let me tell you some facts about this. The first one is that the alpha invariant is actually positive. So the law canonical thresholds are not positive, but it's not clear that when you take this infinite infimum, it remains positive. And it's not too bad if x to prove if x is not smooth. So this is, but it's not clear if somewhat more tricky if x is not smooth. If x is smooth, it is not too bad. I want to tell you one fact. The next fact is that, or next example is that if x is Pn, so Pn is a Fano variety because negative of the anti-canonical is n plus 1 times hyperplane. It's an ample divisor. In this case, alpha of x turns out to be just 1 over n plus 1. Note that this is equal to the law canonical threshold of x comma n plus 1 h. So that's one example of the alpha invariant. So this is the invariant. It's defined in terms of singularities, some kind of asymptotic infimum or an infinite family. And in slide one, I think I said why we care, because it gives a sufficient criterion for K stability. Okay. Are there any questions so far? Okay. If not, I'll move on. So next we'd like to define a characteristic P, an invariant in characteristic P, something that uses the Frobenius map. And the idea is we'll replace KLT. We'll preserve mostly the definition, but we'll replace KLT with a different notion called global F regularity. Okay. Now, K be a perfect field of characteristic P, right? And X comma delta be a pair. Again, this means X is normal, delta is an effective Q divisor. On pair over K. Right. So since X is our characteristic P, so we have a natural absolute Frobenius map. Right. So locally, it's just given by taking a section to the pth powers. We can also iterate this. So we have Fe, where you take r to the p to the eighth powers. And since we are in characteristic P, this is a ring homomorphism. Right? So F to the E is map of schemes on X. So define what global F regularity is. It's slightly technical, but I'll say why this is interesting. So X delta is globally F regular. Abbreviated to GFR. If for any divisor, any effective divisor D, here I mean a way divisor, there exists some E large such that something happens. So we can construct a map. So we have an effective way divisor. So this comes with a natural map from OX to OX of D that recognizes this effective way divisor. Right? So we can take this map and push it forward along the Frobenius E times. Right? So we initially thought of this on the left side of X. Just push this map of sheaves down to the right side along S star E. But now we can compose a map from OX to S star EOX, which is the Frobenius map. Okay, so we have a map like this. And I need to make a slight modification. So instead of for D, we'll apply to a slightly different effective divisor, which is to incorporate delta, which is you raise delta to the p to the e minus 1th power, take ceiling because it's a Q divisor, and then add D. So it's a new effective divisor. It's the same way. It's the same map, but for this new effective divisor. So anyway, so we have a map feel like this. What we want is, so this map, maybe the map splits over OX. And that means that there exists psi right? Such that psi composed phi is the identity, and psi is the map of OX modules. Okay. Are there any questions about the definition? So this is the definition of what it means for this pair X delta to be globally F regular. Notice that there are no resolution of singularity, even if we know them to exist. But yeah. I'm going to the next slide. I'll tell you a fact due to Sweden Smith. So they proved the following fact. So suppose we take a Fano variety over the complex numbers, and we take a Q divisor, which is an anti-canonical Q divisor, and we fix a number t between 0 and 1. It's strictly smaller than 1. Okay. Then they say that x comma the pair td is KLT. So remember, these are over like complex numbers, so we can talk about KLT. If and only if x comma td mod p, so you can take that pair and reduce mod p, is globally F regular for all p large. Okay. So if we fix a t and fix a divisor d for a pair to be KLT in characteristic 0, is essentially is equivalent to it being globally F regular mod p for all large p. Okay. So this is why I think this is one reason why we say that global F regularity is an analog of KLT singularities in characteristic P. So morally they are very closely related, and morally they're like the same. Okay. So motivated by this fact, so the fact that this is a reasonable thing to do, so to replace KLT with global F regularity. So now we'll define the main invariant, the alpha F invariant, or the Frobenius alpha invariant. And I'll make some comments about this definition. So XP, a globally F regular Fano variety over K. So this is, we should think of this as an analog of the KLT condition on Fano varieties that we use to define the alpha invariant. It's slightly stronger, but we'll need it anyway. Then alpha F of X is the supremum for all non-negative T's, such that X comma TD is globally F regular for every for every effective divisor Q linearly equivalent to negative Kx. Right? So I've literally taken the definition of the alpha invariant and replaced KLT with global F regularity. Okay. Are there any questions about this, the definition? If not, um, let's move on to some remarks. I'm going to the sixth slide now. Okay. So the first remark is that in so I want to say a little bit more about how this is exactly an analog of the alpha invariant. Make it more slightly more detailed. So let S be the section ring. So take over some or all and of the anti-canonical divisor, all multiples of the anti-canonical. But if it's not already Cartier, pick a multiple. So this is the cone over. So y equals spec S. So this is the cone over x, comma, this minus RK. So y is an affine variety. So a more precise analogy is that x comma td is globally F regular should be thought of as the condition that on the cone y comma t d tilde, where d tilde is the cone over d, is KT. That's approximate, I just mean analogy. So a more proper way of thinking about global F regularity is that the cone over the pair is KLT. So the reason for this, why this is more proper than what I already told you, is this does not involve any conditions on the coefficients. And so there is a version of local F regularity where we ask for the splittings to only exist locally, but the subtle thing is that we don't expect those splittings to patch up to give us a global map. So there's a subtle difference between local and global. And for local F regularity, that is completely analogous to KLT singularity. But if you want to think about global F regularity, it's maybe better to think about KLT, but on the cone. So the second thing is, so we had a characterization in terms of law canonical thresholds. And an analogous characterization here is that this Frobenius alpha of x is the infimum or all n, and infimum over all d linearly equivalent to negative nkx of what is called the FPR threshold of y comma d tilde, where we take FPR thresholds on the cone. So this is the SPR threshold is the analog of log canonical threshold. It's exactly basically the same thing. It's the largest, it's the supremum of all coefficients you can put so that the pair remains KLT. Not KLT, but this time F regular. But we should actually just put locally F regular, not globally. So I'll not say more about that. But the thing I want to emphasize is that here we are somehow taking um, whatever is analogous to the log canonical threshold on the cone over X. Okay? So that's like a deviation from the definition. But in the third remark, I want to say that this is not so much of a deviation. We were kind of already doing this anyways in the usual alpha invariant. So if delta is an effective anti-canonical Q divisor, right, then the log canonical threshold of the cone, so we use delta over delta, is just the minimum of 1 comma the log canonical threshold of x comma delta. So we're saying that in the usual alpha invariant case, when we are using KLT singularities and log canonical threshold, working on the cone doesn't really make a difference as long as the alpha invariant is smaller than 1. If the alpha invariant is smaller than 1, then the same divisor is going to compute the same, you're going to compute the same LCT on the cone, right? That you compute on X itself. So it's not so much of a deviation as long as alpha is less or equal to 1. So the Frobenius alpha invariant, again, in terms of analogy, is maybe should be thought of as an analog of minimum of 1 and alpha of X. Okay. So yeah, that got a bit technical, but I wanted to say something subtle that's going on here. So no more questions, and we can move on to the main theorem of today's talk. So I'm on slide 7 now. If we are globally F regular Fano, the first part is that the Frobenius alpha invariant is actually positive. This is again not clear. This also follows from results of Kenta Sato, but we give a different proof and some more precise inequalities which to make it positive. The second part is, the more surprising part, is that the Frobenius alpha invariant is at most 1/2 for every x. The third part is that we can characterize equality in part 2. So it's equal to 1/2 if and only if. So the characterization is in terms of another invariant. So this is called the F-signature. of x has this prescribed value. So I don't think I'll have time to define F signature, but let me just say that this is another asymptotic invariant of singularities or of projective varieties, and it is some version of it's similar to the local volume or the local normalized volume that appears in K stability. It's not a precise statement, but it has many of the same properties. So so we should think about this part 3 as saying that having a large alpha invariant is kind of similar, is actually similar or equivalent to having a fixed value, and which is a multiple of the volume for the F signature. So something similar happens in K stability, where having a large value of alpha, the complex alpha invariant, implies that it's K semi-stable, which implies, or which is, I guess, equivalent to the normalized volume being exactly equal to the volume. Okay. So yeah, so if we squint very hard, it kind of looks similar to that. And the fourth part is says that if X is a toric Fano variety, then so if it's a toric Fano variety, we can think of the variety or the complex numbers or in any other characteristic. Okay? It's given by the same fan. Then the Frobenius alpha invariant in any characteristic is actually the same as the complex alpha invariant. So for toric varieties, they're the same numbers. Okay. Yeah, so this is the main theorem for today. So one remark I want to, if I can just make it into part 4 plus 2 implies that the complex alpha invariant is at most 1/2 for toric Fano varieties. And this is already well known in the K stability world. And so this theorem gives like a characteristic P way of proving this fact. Okay. Are there any questions?
Yeah, I'm curious. Did you like compute this alpha for like some specific known varieties in positive characteristic, or it's more like general?
So I can do like 2 examples or something like that. So maybe I'll do one example. I can do that now actually. Yeah. So I was going to do one later. So I can do, or again building on other people's work. I can do diagonal cubic surfaces. Other than, of course, like toric Fano variety, it's the same thing as the complex one. And for the complex one, we have a formula, so we can use that formula for toric varieties. But um, so Okay, maybe I can tell you two examples. Um, so one is uh, suppose it's a quadric X is a quadric hypersurface. By that I mean it's x naught squared plus plus 1 squared. That's the quadric of dimension d. So in this case, we can actually compute it precisely. And this is a non-toric Fano variety. And it turns out it's also again the same as the complex Fano, and it's essentially determined by the index. The second example we can do is of a diagonal cubic surface. Type P3. Um, so here we don't know the precise value, but so we know the following fact. So let alpha p be the alpha of x over fp or fp power. So we can use the same equation over any f or over any p. Right? So what we know about this is that so alpha p is bigger than 0 for p at least 5. Um, so we know that alpha p by the previous theorem can be at most 1/2, but actually it turns out that it's strictly less than 1/2 for all p. The third part is that the limit as p goes to infinity of these alpha p equals 1/2. Um, so I guess I don't know the precise value, but it's saying that it's generally just close to 1/2, and it's approaching 1/2. So this builds on or maybe uses work of Scheidler and Tucker, who did a similar computation for the F signature, and they built on the work of Hahn and Monsky, who had a way to compute what's called the Hilbert-Cohn's multiplicity. It's another invariant. So building on these works, so we can prove this out about the diagonal cubic hypersurface. Unfortunately, the method does not work for any other smooth cubic hypersurface. So this is actually the only example we have. And we can do a few more like this. A few more hypersurfaces, again, all diagonal ones. But that's about the examples I know. Yeah. So I should remark that the complex alpha invariant of the same cubic surface is actually 2/3. So there's one example where the complex alpha invariant and the characteristic P alpha invariant are not matching, also not matching in the limit, and so on. Yeah. But that's expected because there are many Fano varieties where the alpha invariant is bigger than 1/2, but the characteristic P1 just cannot be bigger than 1/2. Or the Frobenius alpha invariant cannot be bigger than 1/2. Okay, so I think I have like 5 or 6 minutes. So maybe I can tell you so yeah, I can state one more theorem. And so okay, maybe so I'm writing on slide 9. So one thing I wanted to say is so the reason for so part 2. So it's a very brief sketch of part 2. It says that the Frobenius alpha invariant is at most 1/2. The reason for that actually comes from the duality for the Frobenius map. So the Frobenius map also comes with an associated duality. So which in our situation gives us a kind of symmetry. So the duality, the statement is that the sheaf form of the Frobenius push forward of anti omega x to the minus n. Alright. So this is the sheaf dual or the OX dual. This is isomorphic to the Frobenius push forward of negative of p to the e minus 1 minus n. It's true for this for every n. So this gives a symmetry in the splittings that we can have in the, let me call this the Frobenius splittings. Which is the reason for this, the Frobenius alpha being at most 1/2. I have a more detailed sketch in the notes, which I'll share after the talk. So if you're interested, you can look at that. Okay. The last 3 or 4 minutes, I'll state one more theorem. So, okay. So if you take a step back, the reason for doing anything with Frobenius and reason for studying, for example, singularities with the Frobenius is that in character. So the definition of global F regularity firstly did not require resolution of singularities, which is unknown in general, but it's actually a little more than that. Even if we knew resolution of singularity, for example, in low dimension. So another ingredient which is required to carry out many of the proofs in characteristic 0, for example, in the minimal model program, are vanishing theorems, right? Like the Kodaira vanishing theorem and the Kawamata-Vivek vanishing theorem. So those things just fail in characteristic P in general. So they fail for most varieties. Oh, sorry, I don't know that. Sorry, they fail in every dimension for even Fano varieties. But it turns out that these kind of Frobenius conditions is precisely what kind of fixes that failure, and it kind of recovers Kodaira and Kawamata-Vivek vanishing theorems. So a version of the Kawamata-Vivek vanishing holds on all globally F regular projective varieties, for example. So that's one reason to work with these Frobenius versions and use the vanishing theorems and the other techniques that it provides to replace the characteristic zero argument. So the three-dimensional MMP basically relies on this kind of philosophy. But another small evidence for why this is a reasonable thing to do is theorem 2, which is, so suppose we have a flat family of globally F-regular Fano varieties. And assume Y is smooth. So having a family of, at least by having a family of globally F-regular Fanos, I just mean, or the Fano part is negative of this relative canonical divisor is Q Cartier and ample and F ample, relatively ample. So we basically have a family, flat family of Fano varieties. In this situation, what we can prove is that the map for any y and y, we map it to the alpha f of the fiber over y. But if you're not taking a closed point, it's not perfect. So kind of go to its perfection. So this is lower semi-continuous. Instead of the perfection, we could also go to the algebraic closure. So, and low semi-continuity means, let me get this right. So at special points, it can only go down, right? And for any point, there is a neighborhood where there's a Zariski neighborhood, a Zariski open neighborhood, where the alpha invariants are at least close to the value at that point. Right? That's what lower semi-continuity guarantees. So, and we can show that for this version of the alpha invariant. And let me just remark that the corresponding results for the complex alpha invariant is due to Bloom and Liu. And it essentially uses Nadal vanishing and other global generation results. So yeah, as I said, Nadal vanishing just doesn't hold in general in characteristic P. But using the Frobenius versions can kind of correct that to some extent and allow us to prove some results like this. Okay, I think I'll stop there for now. I'll be happy to take questions and I'll also share notes.